Okay. First, what I want to let you know is, just some remarks about your programming assignment. And accompanying, I want to have a written part, which you will do on pencil and paper as well. First, the CTL model checking implementation will have 4 components, okay? One is the implementation of the fixed point computation for all the CTL operators, including the greatest fixed point version, where it is suitable for the particular CTL operators. So yeah, so this is basically what you will be, not this one, sorry. It's this one. Yeah, so I'll be implementing this. So I want you to implement the greatest fixed point versions, like for the new Z's, where it makes sense for EG, and ER also. Now, of course, you can express ER as in terms of EU, but I want you to do for ER as well, directly as a greatest fixed point. Okay, so that's what you will be implementing. And after that, based on that, you will be implementing the CTL model checker, which takes the CTL formula, this one. Then you will be extending the model checking to fairness. So that will also be, all of them will be just some fixed point computation of a suitably defined tau. So once you have in your implementation the least fixed point and greatest fixed point generic code, you can actually instantiate that code, to implement all these things. And then, witness generation for EG and EF. For the standard case, without fairness. Number 3 and number 4 we will discuss today. For the return part, okay, this is what you will have. Okay, I already showed you, described you the fixed point characterization for EU and EG. EU as least fixed point and EG as greatest fixed point. What I want you to do is similarly, and we also saw a picture, a graphical thing of how the greatest fixed point computation, what exactly it did in each iteration. Okay. Yes. Okay. So what I want you to do is these 3 things. Okay. First, a fixed point definition, which means a definition of tau, of a suitable tau for ER. Okay. And a proof of correctness that your fixed point characterization is indeed correct with respect to the CTL semantics for ER, and a kind of a scheme for generating, doing a witness generation. General scheme. I don't want you to implement, that thing. So these 3 are what I want you to do as pencil and paper exercises. Today, I will be discussing the proof of correctness for the EU case, okay? And I want you to recreate that proof scheme for ER on paper. So what I plan to do today, or at least the topics that I want to cover, time permitting, are all these things. First, witness generation scheme for EF and EG. CTL model checking with fairness, and how you would do a formal proof of showing that your fixed point characterization computation via the Kleene iteration corresponds to computes exactly the set of states that is defined by the formal semantics of CTL. Okay, that is this. And if time permits, we will see SAT-based model checking. What you have done right now is symbolic model checking using BDDs. Okay, a complete symbolic model checking for CTL. Using fixed points, and the fixed point being implemented as BDDs, and how you could do that using SAT-based techniques. And that's what I plan to cover today. Okay. So we saw that what exactly a counterexample for CTL is really can be reduced to showing it's whenever you have an AG, a universal CTL operator, you really want to produce a witness to the negation of that, which when you take the negation, it gets converted to showing a witness for an EG-EF formula. Okay, most specifically EG-EU. EU formula. Okay, and for EG-EU, you will just show a witness, for EG and EU. That's the convention for doing it. So here are some observations about CX. I think I've mentioned this at various points in the lecture. The claim here making is every witness to EG of F and EF1 until F2. Every witness, as a matter of fact, okay, this claim is applicable to linear time properties, LTL also, is lasso shaped. Okay, every witness is lasso shaped as long as your Kripke model is a finite state. Why? For finite state systems which have left total transition on every finite path, or on every infinite path, the state eventually has to repeat, right? Because there are only finitely many states. So once it repeats, you can then construct a cycle, okay, from that. Okay, so that will be a lasso. You can construct a lasso out of, make a lasso out of that path. Okay, a lasso, just for completeness, has a cycle and and a tail, okay, and a finite tail starting from some start state leading to some state on the loop part. Okay, and the tail part, the finite prefix part, can have repeated states also. But once you get a repeated state, you can always make a loop, and making it a lasso. Okay, and that's the kind of paths, because this so that's the kind of path that we are want to generate as witnesses to EGF and EF1 until F2. Now, for left total finite state systems, every cycle of course must be a part of some maximal SC. Okay, so the loopy part of that lasso has to be a cycle in some SCC. Okay, so a witness to EG of F, witness to F1 until F2 is easier, and we kind of already discussed that, I think, last time. So witness to EG of F is an infinite path on which every state is an F state. So a witness to EGF must be a lasso in which every state is an F state. First of all, I hope you understand what I mean by lasso, correct?
Yes.
Okay. So a witness must be a lasso in which every state is an F state. That's a finite tree-6 of F states, ending in a state, and since a cycle has to be a part of an SCC, in which, and an SCC in which every state is also an F state. I can recall that this is how if you recall, the explicit state model checking we actually implemented. And the greatest fixed point also, eventually the fixed point ends up having these kinds of SCCs embedded in the fixed point, which is a symbolic representation of the states representing EG of F. Okay. So what you really need to compute is this kind of a lasso, okay, which from some initial state will go through a sequence of F states, ending up in some SCC, and the witness will also have to form a cycle. We have to get a cycle through that SCC. Okay, so that so once you pick any cycle in that SCC, you have that lasso. So that's kind of the proof for saying that a witness to EG of F is always a lasso. Now for EF1 until F2. See, for EF1 until F2, given you already have identified the states that satisfy F2, that is given that F2 states exist, so one can always construct a witness path for EF1 until F2 that is finite. Why? Because you have to look for an F1 state, okay, that a sequence of F1 state that ends up in an F2 state. I'm assuming that there exists an F2 state. If there does not exist an F2 state, there's no question of producing a witness. Okay, so now you can always construct the finite a tail. Why? That's because, I mean, it's, of course, the sequence of F1 path leading to an F2 state can be infinite, okay? But if it is infinite, every infinite path in a finite state system, as we have said, must be a lasso, okay? In which every state in the loop is an F state. Therefore, you can get rid of these repeated cycles. So, and you can always construct something in which the loop part traverses it only a finite number of times, and that's why it is enough to look for. You don't have to look for lassos for EF1 until for finding a witness for EF1 until F2, especially if your starting point is an F2 state. That's why you were able to compute the fixed point by computing the predecessors until you reached a fixed point. Because once you reach a fixed point, it will cover all the finite prefixes, F1 prefixes leading to F2, but also those things that may have loops also will be in that in that thing. But from that kind of a thing, so that's why you could generate a witness to F1 until F2 fairly easily by saving the intermediate results of the taus at each step until you reach the fixed point, and then you can pick. You could trace the thing forward. Okay, once you reach a fixed point, then you take some one start state, and then you pick something which is a successor to that. Okay, I think this is the what I had. I think I had gone through this last time. So you run, as you run the fixed point computation as part of the model checking, you will save all these concentric circles, you would have eliminated all these things in the dotted circle. So you pick a state, and then you could do a forward simulation, okay, actual enumeration of a state, take its successor that is inside the thing, and so you can do that. I mean, you can do that using BDD implementation as a BDD checks, okay, of each of these. Once you have BDDs representing each of the tubs, and that's what you're supposed to do in your implementation. Yeah. Okay. So is this clear? Any questions here? Of course, there is some detail which you will have to fill in as to once you pick a state from here. How do you pick a state? You can pick that state which is at the intersection of that is in the initial state as well as in this fixed point. Okay. If that's an F2 state, you have a witness. Okay. If not, you'll have to pick an F1 and then compute its successor that is in tau of I-1 and so on. So this is something that we discussed. Okay. So the detail that you have to figure out is how exactly you will implement that and how you get the next state in each of next state in that lasso shaped. In this case, just the prefix leading to F2. If your initial state itself is not F2. Okay, that is the detail that you'll have to fill, figure out in your implementation. Okay. Now, how would you do it for EG of F? That's the question that I had wanted you to think about. Okay. Any ideas? So here it is. This is the fixed point computation, a picture showing the fixed point computation for the greatest fixed point computation. So here, since you're expressing it as a greatest fixed point, you are getting rid of those states that lead to something that does not satisfy EG of F in one or more steps. And that's what you're doing. And when you're done, what you have is, see what is here. You have all the lassos things in your fixed point. Okay. I mean, the states that you have left in your fixed point when at the fixed point are exactly states that are either on an SCC, okay, every state of which, is an F state, and there is a path leading from itself, or there is a state, which is, on the finite prefix leading to an SCC, which is into lasso. Okay. So here there is no, especially if you're implementing EGF as a greatest, fixed point, you will have to use this fixed point that you get. Okay, there's no point in actually taking these things. Okay, so once you reach your fixed point, you will have to, of course, you will check in the model checker if your initial state, set of states is indeed contained in this. In this fixed point, correct? It has to be completely in it, because this is the set of all states that satisfy EG of F. So what you will have to do is one way of doing it is you have to pick a state which satisfies pick an initial state that is also in the fixed point, okay, and kind of generate a trace, okay. From that, I mean, like an enumeration, and you will have to kind of, one, if you do really enumeration, you will have to keep, taking the, it's a successor state from it, kind of saving it until you, saving all the things until you see an already visited state. Okay, that is that you could do that. Okay, I mean, that doesn't give you the shortest lasso, but you really have to generate a lasso, and every lasso is in that fixed point. So you could implement something, kind of an iterative method that picks a state and initial state, and checks and enumerates that thing until you get a lasso. That's the simplest way. Of course, that does not guarantee the shortest, the shortest path. Okay, but that is a method. Now, I think to get a shortest path for EGFF is not that easy. Okay, now we can in your implementation, I'll be happy if you could figure out a method. Okay, not necessarily a shortest path, but use this fixed point representation as a BDD and do some use that to kind of enumerate this or extract this lasso, which is a witness to EGF from that. Okay, so and I will have you work out the details of your counterexample generation. I'll be happy to discuss each of you. That's the one for which I have not given all the details. Okay, for the rest of the components of your programming project, what is covered in the class lecture, can be easily converted into a code. Okay, so if you have questions about this, filling in the details of the counterexample generation for F1 until F2, I've kind of discussed the scheme. So for this, it is not, there are some details that you have to fill out. But if you want to discuss it after, you come up with, either you do the complete implementation without discussion. But if indeed you have doubts or issues, you come up with a scheme on paper, and then we can discuss it, with you before you convert it into an implementation. Okay, so that's where I want to leave. I don't want to give all the details of the thing. Okay, so I kind of thought about generating the shortest thing using some symbolic methods, but I think there are no very easy methods. Okay, to see what that thing is. Okay, so I will have you think a little bit more about the scheme, and in a future class, I will revisit this thing. Especially now, I'm not requiring you as part of the implementation to generate the shortest counterexample to EG of F. The method that I showed you for F1 until F2 will automatically generate the shortest counterexample. And I want you to think about why that is the case. Okay, the method where I showed you, where you save all the intermediate tau points leading to a fixed point. Okay, because what you're doing here is kind of a breadth-first search in which you're accumulating all the states that reach in one or more steps in a single tau iteration, and that's why you're able to generate. But that's not the case here. Okay, so think about that counterexample generation, and we will discuss that in a future class after I've given it some thought. Okay. Any questions here?
Not regarding this, I just wanted to know, what does forward symbolic computation mean?
Yeah. So what I mean is, okay, so let me, yeah, so that's, so this process of extracting a counterexample is what I'm calling as forward symbolic execution of it. Why do I do that? How do I? Okay. So what I'm saying is tau 1 is F2. You're saving that. What is tau 2? It is the union of this concentric circle, the first circle here, and F2. The third thing is tau 3 is the second concentric circle union with F2, and so on. So you have BDD representations denoting, characterizing those states. How do you think about, how do you extract a counterexample? That is a witness to a state in your fixed point. Your eventual fixed point will contain this tau I, okay, which is the union of this biggest concentric circle and F2. I mean, not the union. I'm sorry, no, correct. Yeah, so it is correct. Yes. Okay, so it is that union of this is what the F1 until F2 state is. Okay, because every state in F2 is obviously something that satisfies the condition. Now, what I mean as forward computation is, you will have to, the task of generating the witness path leading from a state which is an initial state and in this fixed point, that in 0 or more states, an F1 state in that fixed point, that in 0 or more states, 0 or more steps lead to F2. That task is what I call as forward symbolic execution. Now, I don't know if that is the right term, because, well, the reason it's a bit of an execution, but it's symbolic, is because how do you do that? Okay, I'm actually giving you those details. Okay, so I'm to answer your question, what I call a symbolic forward computation, it is that task of extracting the counterexample. Okay, without actually revealing all the details, if I want to answer your question, why do I call it symbolic? Because you have to now pick a state that is in the intersection of I and this one, okay, the fixed point. So after that, you have to check, is any of that state already satisfies F2? Then you have a witness. That is the shortest witness. If there is no such thing, then you'll have to pick an F state in that, and then compute a thing which goes to, in one step, to something which is inside tau I minus 1. Okay, and then check if that is F2. Then you have a a path, F1 until F2 path, which is a witness, VU. That task of doing that, okay, is now I'm doing symbolically. Why I call it symbolically? Because I'm using the saved representations of the intermediate fixed points and then doing some satisfaction kind of task to extract a state. Okay, that is the detail that I want you to figure out. And the reason I call that symbolic execution is because it manipulates BDDs of the initial state, of the state satisfying F2, other these predicates which are already have been saved as BDDs. These predicates representing each of the tau i's. Okay, and then you are traversing those things to extract a counterexample. Does that answer your question?
Yes.
Okay. How do you do that? You have to pick an S0. Okay. So your task is to pick an S0 to SK, where that K is something that is smaller than or equal to this I, such that it is S0 through SK minus 1 is F1 and SK is F2, is an F2 state. Using these intermediate fixed points. That's what you have to figure out. And because that uses all these symbolic representations of the intermediate state of your fixed points, that's why I'm calling it symbolic forward execution in this case. Okay, I mean, it's always forward execution. So, I mean, kind of forward execution. So here also, when I do that for this case, I mean, you will have to do that some kind of a forward execution inside this. Once you reach this computation, now you have to extract a lasso from that. The lasso that you're looking for, which is a witness to EGFF, is there in that, embedded inside that fixed point. Okay, but you'll have to do some, this, what if you call computation, to either thing. I mean, the extreme thing is you could enumerate it, okay, by picking one state and so on, but that will not give you the shortest path, okay. Extracting the shortest path for EGFF is non-trivial, okay. So I will, that's what I would call it, okay. So yeah, so I'm not giving you, any scheme for this, okay. But what I've told you is, in the worst case, what you could do is you can pick one state and compute, enumerate, okay, its next state, etc., saving it all the way until you see an already visited state. Okay, that is explicit enumeration. Okay, and you could use maybe this fixed point to ensure that you stay within there. Okay, that you don't wander around. Okay, that is where you will have to use the fixed point generated. Okay, I think you can use that. I hope you are getting some ideas. Okay, so where you will have to figure out. Okay, so you will have to, when you do that enumeration, it helps you to stay within this. Okay, because any lasso that you have to extract as a witness has to be, and every state on that lasso has to be on this, has to be in this fixed point. Because you've removed all these things which should not be, which are not states as for each. Yeah. Yeah. Okay. So what else? Then that is done. Now I'll have to talk about checking, model checking on the fairness. Okay. Now, before I do that, I want to revisit this thing of greatest fixed points to compute EG of F. See, the tau for this is F and EX of Z, okay? So I think I made this observation. When you remove all these things, okay? So what is, okay, every state on this SCC, you notice, is a state such that it satisfies F and EX of F. Right? As a matter of fact, even these things are like that. Certainly, every state in this is satisfies F and EX of F. And so do all these states that on this tail, which lead to this thing. That's what you're using. So, in other words, every state on this, on which F and EX of F kind of repeatedly they hold, will eventually lead to something in which F holds infinitely often, because it ends up in an SCC. Okay? So what you're removing are things that those SCCs in which F does not continuously hold. Okay, is what you are. I'm sorry, I shouldn't have said infinitely often. If it continuously holds, obviously it holds infinitely often as well. Okay, so you're using this thing of F and EX of Z to kind of remove these SCCs and states that lead in one or more steps into an SCC on which F does not continuously hold. In the sense, every state satisfies F. Okay. Now, so here it was standard model checking. Therefore, what you will have to, if you want to do model checking under fairness, what you'll have to do is you have to kind of limit your, you have to find a way of limiting your these strongly connected components inside your lassos through this fixed point computation, where a predicate, a fairness predicate, satisfies infinitely often. Okay, so you could see that it will be something like this. Okay, in this fashion, and that is the idea that I'm going to exploit in doing this. Okay, so before I show this, this is the picture for doing multiple predicates. Okay, I will first do so. As you just to recollect your memory, what you have is, so your fairness constraint is expressed as a finite set of predicates, correct? So you will have to eventually end up something like this in your fixed point. Things where you have states that are either part of these kind of SCCs on which one of the states satisfy P1, P2 hold infinitely often, that some subset of the states, or something that leads into that thing. Okay, and that's what I'm going to illustrate. So first I will show you for the case where you have just one state, and then I will extend that to multiple predicates, or one predicate, and then I'll extend that to multiple predicates. Okay. Yeah. Now, once again, I'll be computing this as greatest fixed points. Okay. So the idea is, see, if you look at this one, look at this condition, f and ex of ef until this p is the fairness predicate here. Okay. See, the unfair, SCCs are ones, in which you will have an sequence of f states, but it will lead to something in which every state ends up satisfying not of p. Okay, but p is some other predicate. In the case of EG of f, I mean, we just wanted an f, an SCC of an f. Therefore, if you look at these kinds of things, so every state in that, okay, in this strongly connected component, if satisfies is an f state, or something in which the next state satisfies f until p, okay, where p is the fairness predicate, right? Because there is an f, and there is a one of the states satisfies p, okay? Because if there is, this is all the states f until f and ex until f until p, because every state is such that f until p will satisfy, because if there is even one state that satisfies p in this SCC, every state will be one in which f until p satisfies. That's why it will satisfy something which is an f state, as well as something in which which satisfies the next state is will satisfy ex of there is a path on which f until p gets satisfied. Okay, so you want to keep only those things. Okay, so, and you want to eliminate all those things that are in a loop like this, in which there is every state is not p, or either it leads to every state leads to some not f, or there is no path from that, in which f continuously holds. I mean, even if f continuously holds, it ends up in a something which is not fair. Okay, so that's why if you had your z, if you had your tau as f until, I mean, it should be those, it should satisfy, it should be only f states, okay, because we are computing a fair version of EG of f. Okay? Obviously, every state has to satisfy f, and those that in the next state will satisfy EX of f until z and p. Okay, if you had that, then you would that would be the right thing, because you would end up in each step eliminating these kinds of you will end up unfair, once you reach a fixed point, you will end up eliminating unfair things in which p does not hold infinitely often, or states in which every successor is leading to such a thing. Okay, so and that's what is I've shown here. So yeah, so if you look at this one just in one step, f until f, and in the next state, I mean, there exists a next state in which every state satisfies f until, I mean, there is a path in which, there is a state, a state in which there is a path in which f until p1, okay, where p1 and p2 are predicates, okay. So, those are things in which p1 and if every state on this thing satisfies that, it'll be those in which p1 and p2 will hold infinitely often. Okay, so what you need is a tau z in which you have every state has to be an F state, and it should be such in the next state. What should be true is there must be a path in which F until Z and P1. So Z is this, recursive thing that you use to keep things that only satisfy this one in one or more steps. Okay, so with this tau z, so you could so for each of the predicate you should have this condition ex ef until z and p and p1 p2 etc. Where p1 and p2 are the fairness predicates to hold them. Okay, so because then what this will do is in each step it will only keep, okay, it will eliminate, for example, right in the beginning it will in one step it will only it will keep only things self loops in which P1 and P2 both hold, because they certainly are fair paths, right? Self loops. Or in two steps it will eliminate things like in one step it will eliminate things like in which there are self loops in which not of P2 holds good. Okay, in two steps it will eliminate things like this. Okay, in which maybe P1 holds infinitely often, but P2 does not. Okay, and and anything that leads in one or more steps to one such thing, because you see, if you had the entire in the explicit state model checking, you had the luxury of identifying these fair, strongly connected components by observing all the states, by enumerating all the SCCs. But in symbolic computation, you don't have that luxury. Therefore, the way that you do is by kind of indirectly eliminating things that violate your because so this if every state, I mean in the next state satisfies ex f until things that in one step will either end up in an SCC, it's kind of the size, or it will be not a fair SCC, and that's what is happening here. So and since the size, and since you don't know that SCC cannot identify, that's why I use this trick of eliminating the negation of that condition. Okay, and that's what is happening here. Okay, so you are embedding, as you can see here in this case, you're embedding inside a fixed point operator. Here it's the greatest fixed point, a CTL operator itself, which is an F until Z, I mean, some Z until and a P1 kind of a thing. Because if you took the negation of this, you will see you end up, okay, so what you will end up retaining is only at the end in your fixed points, only the SCCs that are fair, on which P1 and P2 happen infinitely often. So as you can see, the negation of that is one in which that fairness condition, forever, it'll have those SCCs which are, in which the fairness condition does not hold good. That is, the negation of, I mean, infinitely often is expressed as G of F. The negation of that is the persistence thing, Fg. Okay, and you see, Fg is not representable in CTL. We already proved that. Okay, therefore, that's why you cannot represent the CTL. But what is happening here is by combining a fixed point operator, fixed point here, new Z, and a CTL operator in a nested fashion, you're able to express this, express that. And that's what you're doing, because all the CTL, the tau that you've seen so far, what you had was only, it was implemented, the tau Z was being implemented in terms of EX or AX. Whereas here you are using a CTL, an infinite CTL operator. Okay, a CTL operator whose satisfaction path, could be an infinite path, like until or a G kind of thing embedded inside this, and that's why you are getting that you're able to do this. But the thing that you will have to understand is what you're doing is you're by picking the your tau Z to be a conjunction of this EX, F until Z and P1, and the Z, and you're starting from true, you're kind of eliminating in one or more steps that all the states which don't satisfy this condition. Okay? And when you have a condition which says that every state should be such that its next state should satisfy F until thing, and when you do the fixed point computation, what you're doing is eliminating things that get violated, that are witnesses to the negation of this condition in one or more steps. And the negation of this condition in one or more steps, when you reach the fixed point, it will be those that are things in which you have SCCs. You would have eliminated those SCCs in which they will never, this fairness condition will never be satisfied infinitely often, and that's what will happen here. So you could, through this, by reviewing this picture, so maybe you don't get the complete all the details here, but these, I hope these, you have to review these pictures and kind of simulate the tau 01, a few steps to see that indeed you are eliminating what I've shown here through that computation. Start with the single predicates stuff, okay, case, and then go to the multi-predicate case. So the tau z for the general case is this one, okay, where your fair condition is computed as a greatest fixed point in which every state is such that F, it's an F state, and your next state you will have will be such that F until Z and PK should hold it, okay? The negation of this part in here should be eliminated. Every state that leads to this in one or more steps. Okay, so that is the thing. So I guess I spoke too long without stopping. So any questions? You have got some idea? So you see, when you implement this, it will have unlike all your previous implementation, like I already said, you would be calling another fixed point iterator, because F until this itself, each step of your fixed point, outer fixed point iteration will be invoking another fixed point computing loop. Okay, so this is an expensive thing. Okay, because it has nested fixed point computation thing, okay, which is what is not expressible in CTL, and that's what you're doing here. Okay. Yeah. So if every state satisfies F until every state in a kind of a thing that forms a cycle satisfies this condition, then it'll end up satisfying P1 infinitely often. And then I'm taking conjunction of these things. And therefore, that means that each of the negation of it are those in which neither P1 nor P2 will be satisfied infinitely often. Okay. So any questions here? Yeah, review the slides, think about it. And if you have questions, please come back, okay? Make a note and then okay, so what is my next thing on my list? How do you do a proof? Okay. Yeah, sorry. See, what you really want to prove is this. Okay, see, for simple things, I mean, maybe even for CTL operators without fairness, you could probably get an intuition. But since this fixed point computation, the way that you do is somewhat intricate, to say that the fixed point actually of that tau actually contains only those states. It contains every and only those states that satisfy the which would satisfy the corresponding CTL, the formula which is rooted at that CTL operator is not very obvious. Okay, so and that's what I'm trying to show here, and I think it is useful for you to kind of understand what the proof scheme is like in this case. But maybe some of you have seen this kind of proof before, but it's proof by induction, okay? Because the way that you compute, it's kind of using two kinds of induction. But first, are you clear as to what you have to prove here? On the left side, proving equivalence between two sets of states or formulas representing two sets of states. On the left side, I'm relying on, using the semantics of CTL operator, CTL logic, to define, which defines all the interpretations, all the states that for which that make F1 until F2 true. That is based on by looking at states and paths originating from that state. So you will have to, that is defined in terms of that. On the right side, what you have is a tau whose fixed point is computed by this cleaning iteration, by applying that tau to itself starting from false. This is the case I'm showing you for computing least fixed point. As part of the exercise that I've given you, you will do that for greatest fixed point. But I'm going to show you the proof, which is there in the book as well. You can read it. So on this side, you are using iteration over tau. On this side, you are demonstrating the states using paths. The size of the path is what you will have to. So basically, what you will have to prove is the following. See, what are you doing here? You're computing the fixed point is actually, when I say it is computed as a cleaning iteration, what are you doing? the limit of that tau chain is actually the union of all the tau i's, starting from 0 to some n. In the case of finite state system, it is some finite n. Okay, and that's the when you reach the fixed point, you would have done the union of all those things. So what I'm so that's what. So there are two things that you have to show that those states that you end up that are contained in the limit of this tau chain, which is a union of these things, starting from bottom, which is false, is included. Every such state is one that satisfies E F1 until F2 as per the semantics. And the other side is that it does, I mean, every state in this, F1 until F2 is indeed included. Every state that satisfies F1 until F2 is also part of this. These are the two things that you will have to do. Now, this one can be shown by inducting on the length of the tau chain. That is the number of iterations that you require to reach your fixed point. Okay, so you will, because it is the limit is the union of all those things, you will have to show that every tau I, starting from 0 to n, less than equal to n, is contained in that. And since the union, the limit, is the union of all those things, that will be contained in that as well. And that is the method that is used. Okay. That is, it's done by induction on I. Now, here, you will have to use induction on the length of the prefix of the path under which F1 until F2 is satisfied for S. Okay. So for every state, there is some, because you have to look for a path originating from that state, you have to ensure that satisfies a certain constraint. So in trying to do this, you will have to, for every such state, that for which the interpretation, the path that that is able to show that it indeed satisfies that condition is say n. By inducting on that, you will have to show an existence of a corresponding I on the right side. I mean, a corresponding number of I, for which at which you can compute the fixed point tau of. Okay? And that's how by using clean iteration. So those are the two things that you'll have to do. Okay. So I will show the steps here. First, let me take the second one. Yeah. So the second one again. I'm showing that every state that satisfies this formula as per the formal semantics, for every state, there is a n, that it is true for some, some n, okay? So by induction on the length of the prefix of the path under which F1 until F2 is satisfied for us. So, for example, those paths that satisfy, those states that satisfies this are states in which there are paths of this kind. S1 to Sj. Sj satisfies F2. And every S1 through Sj minus 1 will be an F1 state. And here the length of such a path is, j, okay? And that is what you're inducting on. Okay. See, if j is equal to 1, what are those states that satisfy, that are included in this? Anyone? Ratnakar?
We just set it to F2, right?
That is correct.
And
yeah, that's exactly right. Yeah. So those are the states in which F2 is true. Therefore, you can get those things in one step because the 0th step is false. Okay, this you should read as I is equal to 0 to 1. Okay. So 0 is always, tau 0 is false. So there is an I, So those states, you get them, okay, in one, in the first iteration of that Kleene iteration itself. Okay. So, and that's how it's done. Okay. So now, yeah, that's because your tau is defined. That's where you will use your tau definition. Okay. That's why, given a tau, okay, to convince yourself that indeed it computes exactly those states, you could kind of simulate these tau chains and convince yourself. Okay. And by following to these proofs, you can convince, okay, yourself that the fairness tau, the tau that I define for fairness, indeed is correct. Okay, so then what you'll have to do is the tau itself is defined using that expansion law. Okay, so is this one. So this is what you do. So from f tau 0. I've plugged in tau 0 here, and tau 1 is exactly this, and f2. So which is this is false, and this has f2 or false, and which will be f2. The induction assumes this claim itself, that this subset of this holds for every state that satisfies the left side here, and the paths from S that satisfy F is less of some length n. Then you show that this claim holds good for those states for which you need to look at a path which is of size n plus 1. Okay. Yeah. So assuming. Yeah, so you have to prove that if S1 is a state in which there's a path S1 to Sn plus 1, that is of length n plus 1, for which all the n states satisfy F1 and n plus 1 satisfies F2. They have to show that there exists a value of I at which in the fixed point computation that state would have gotten into the fixed point. Okay, that's what you will have to show. So once again, you will assume that this state S2 here, which you have extended into an n plus 1 length path, for that there exists an n. Such that tau n, the tau n in the nth iteration, it would be in the nth iteration of the point in the tau chain. And now you will use, and since your transition relation S1, S2, you will have to show that S2 is actually a successor. Okay, that's what you will have to show. Since in this sequence S1 and S2 are related by this transition relation T. So, and this one says that states S1 should satisfy F1. This one is true. Will be inside the left side only if S1 satisfies. Okay? And then there is S2 is a successor of S1. Okay? And that's what this thing has to. And that is what you will have to show. And since that, tau n, Ex of tau n, indeed, S1 has to satisfy F1. And what you do is, S2 is such that it is a successor from S1 for which this tau n of false should hold good, because it is saying in the next state, which is S2 is a successor of S1. And that is true by induction hypothesis. And that's why, you will get that. Okay. So that's how you'll have to establish the proof. Okay. Therefore, that here, I'm sorry, this should be S2. So because of this they are related by this transition relation, and that will satisfy Ex. And since that S1 is such that Ex of that is satisfied, S2 will belong to, and I'm sorry, here it should be S1. So S1 will belong to tau n plus 1 of false, because this is tau applied to T applied to, in one step, you're applying the tau function, which is exactly one step expansion of the tau is what I'm showing here. Okay, so the other part is kind of easier. So what you have to show is for every I in n, the number of iteration that you take, tau I of tau 2, when it terminates, is part of that. So you have to show that for every I, tau I of bottom false is included in that. So once again, induction on the length of the tau chain. So you will have to first show the tau of false. False is obviously included. False implies this. So in one step, you will have to use the one-step expansion of tau to show that this is there. And then for induction, you will use for every n less than or equal to 0, tau n of false is inside that. And then you show that tau n plus 1 of false is also inside EF1 and F2. So here you will have to make tau n plus 1 is tau applied to tau n. And then you expand this, and then you get the Ex. And since this is something which is obviously satisfies EF1 until F2, because this is, you have to use induction hypothesis here, okay? Because you have, if it is F2, it's an F2 state, then it is obviously included. But if not, it is something which is F1 and it leads to an X state in which tau n is of top bottom is included in this, and that you get by your induction hypothesis. So that's how that you do. Yeah. So yes. So yes. In one side, you will have to, yes. What you induct on is something that you have to keenly observe, and then in the one direction proof, you will use the definition of tau z, tau, okay, and expand that to show your inductive case. In the other thing, you will use the relation for transition relation, okay, in that thing to show. Yeah. So yeah, and my goal in having you do it for R is so you will get a flavor of recreating this proof for greatest fixed point. Okay, and that's how you will have to express R as. Okay, so I want you to do for ER. Okay, kind of reconstruct that proof, similar proof for ER. Okay. Any questions here? Okay. I hope, yeah, do take some time to review that written part and the components of your implementation that you had. If you have any questions, if you are having any technical issues, then you'll have to, you can contact me or Diganta, okay, to get clarifications. So if there are no more questions.
I think we have the
Yeah.
assignment uploaded yet. When do we
No,
need
I will
to
do it
submit?
right away. I've kind of informally told you that. Okay. So I will exactly upload this. This is all, I mean, I'm going to give you, this is all I'm going to upload. Okay.
Oh,
So I don't think I've described it enough in the class, and this is what I'm going to upload. And if you have any questions, you'll have to do. I think there are some questions about what you need to submit, what examples you need to check it on, and so on, as part of the deliverables for your program. That will be made clear. And I hope what the inputs are and so on, they were made clear. But this is what I'll upload. So, and I'm not going to be doing any more, because if you have questions and you want details, you can ask one of us. This I will upload. Maybe, I don't know, maybe, I mean, in the last time there's a class that was big, I mean, I had made a written assignment, I can upload that. And I don't know if that has more details. Okay, that, I guess, Paramal, already you located it, no?
Yes, sir.
Yeah, I can upload that. So, which is a little bit more descriptive than what I have here. And the assignment is due in 2 weeks, okay?